Hi, in this video I'll introduce the Perceptron. Remember, we're in the supervised learning setting where we consider an unknown target function f from x to y. To simplify matters, we'll have y be -1 and +1. In this way we'll have a binary classification problem. We'll have only two classes. Now, in this problem we'll also have a data set. So the data set will have the form x1, y1, all the way up to x capital N, y capital N. So as an example, we could have x to be R2, and then I'd be able to visualize a data set in 2 dimensions. So a data set might look something like this, where I use a plus to indicate that the point is in the +1 class, and a minus as the point is in the minus class. And then the location in the coordinate system corresponds to the entries of the 2-dimensional vector. Okay, so if this was my data, I would be able to then the target function could have been this guy. This could have been the target function. I probably won't know, but let's just suppose this is a target function. Then what I want to do is I want to approximate the target function by some hypothesis we'll denote h. So it would probably be sufficient if I could find this guy. This would probably be an okay approximation of f. But we'll be a bit more formal in what we mean by approximate. So we'll define an error measure. Error measure. So this will be the sum over all the points. So we'll sum from the first point, the second point, all the way up to the capital Nth point. And then we'll consider, well, what does the hypothesis say on the ith point, and what should it say? So y1 is the true label of the point. This is the class the points belong to. And h of xi is what our hypothesis predicts on this point. So we'll have the indicator function of if these are different. So this is defined as 1 if this condition is true, and 0 otherwise. So what this sum says is, it says, well, let's consider all the points, and then I'll add 1 to the sum if my hypothesis misclassifies the ith point. So we'll also have a 1 over n here. So this will make this thing in 0, 1. So if I classify all points correctly, then this sum will be 0 for each term, and the entire thing will be 0. If I misclassify everything, this sum will be n, and then dividing by n will give me that it's going to be 1. So this will be my in-sample error rate. Okay. So then I'll also have a hypothesis set. And this will be all the functions h of x of the form sine w transpose x. So we defined the error measure for the perceptron, and we defined the hypothesis set for the perceptron. So let's go look in the IPython notebook. So the first thing you'll see is a brief explanation of the perceptron. This is roughly what we just covered. After this, there'll be a few lines of code. If you run these, they'll import the Perceptron dataset. You'll see this dataset can be separated by a line. This is what we call linearly separable. After this, I added a few lines of pseudocode for the Perceptron learning algorithm. What the algorithm does is it initializes the hypothesis randomly. So remember that the hypothesis is represented exactly by its weights. So it'll be initialized by random, and then we will take a point that's misclassified. If there's no points misclassified, we'll have classified the dataset correctly. So probably there'll be one. If not, then we're done. So we'll take such a point, and then we'll use this point to update the current weights. So I have a code here for the Perceptron. I coded it as a class, and if we run the code on the dataset above, you'll see visualization. In each step on this visualization, all the misclassified points will be colored red. The algorithm will then pick a point and move the line towards that point. So this is the point that's always be kind of displayed, and the arrow will indicate the direction that the line will be moved towards. So this is a Perceptron learning algorithm. You could try to play around with it, maybe make it sleep more in each step or sleep less, so the visualization looks a bit nicer. So suppose we now have data that looks like this. This data can't be separated by a line. It's not linearly separable. If we run the Perceptron learning algorithm on this, it would never stop. It would run forever. You might be tempted to run the Perceptron learning algorithm for a lot of iterations and then take the best one. This is the idea of the pocket algorithm. Run the Perceptron for several iterations, compute the performance of each iteration, and then return the one that gave the best error. If we do this, it will look something like this. So the dashed line is now the best weights found so far. So currently this is probably the best, and this is the one that will be returned in the end. This algorithm is called the pocket algorithm because you can think of it as putting the best weights you found so far in your pocket. Great. This is all I wanted to say about the Perceptron and the pocket algorithm. See you in the next video.